video covers Module 7, Part 4, which is about adding, subtracting, multiplying, and dividing radical expressions. We will have to remember everything we learned in Part 3 about simplifying radicals as we go along. So please complete your guided notes while you watch this video. So when I have two or more square roots that have the same radicands, meaning that's what's under the radical, we call them like radicals. And we treat these similarly to like terms in an equation. You kind of like a variable, and we can combine them. So for example, if I had 7 root 11 plus 6 root 11, that would give me 7 plus 6 root 11, so I'd have 13 root 11s. Very similar to as if I was working with a variable. But we have to remember that one extra step, which we covered in Part 3 about simplifying radicals. So for instance, if I had 2 root 18 minus 5 root 2, the first thing I need to do is simplify the square root of 18. Well, I know 18 factors into 9 times 2, which is 3 times 3. So I could rewrite this as 3 squared times 2. Well, square roots undo squares, so that 3 gets to come on the outside. So I'd have 2 times 3 root 2 minus 5 root 2. Well, 2 times 3 gives us 6. So I have 6 root 2 minus 5 root 2, and I'm just left with root 2. So let's practice solving some of these examples. So if I have the square root of 5x minus 7 square root of 5x, those are like radicals, and I can't simplify them any further. So I'm going to take this 1 minus 7, so I get negative 6 root 5x. For problem 2, I have 7 root 3 plus the square root of 12. 12 is 4 times 3, so I can simplify that because 4 is a perfect square. So I would have 7 root 3 plus the square root of 2 squared times 3. Well, or if you knew right away how to simplify that, we would have plus 2 root 3. And now I can go ahead and add these. 7 and 2 gives me 9 root 3. For problem 2, I need to simplify both of these because 20 is 4 times 5. And 45 is 9 times 5. And that x doesn't have a partner, but it sticks around too. So I would have 2 square root of 2 squared times 5 times x minus the square root of 3 squared times 5 times x. That becomes 2 times 2, because this 2 gets to come outside, square root of 5x minus 3 square root of 5x. That is 4 root 5x minus 3 root 5x. So I'm left with just root 5x, right? These problems take a little bit longer because we have to simplify those radicals. I'm going through and doing the step-by-step of how to simplify the radicals for the first few examples, like how we did this step-by-step. But if you know the square root of 18 is 3 root 2, you don't have to show your steps. If you know the square root of 24 is 2 root 6, you don't have to show your steps, right? 4 times 6 is 24. 4 is a perfect square. It comes to the outside, 2 root 6, right? You don't have to show your work, but you should at least practice. But eventually, you'll do enough of these so that you'll know, like, oh, the square root of 12 is 2 root 3. The square root of 20 is 2 root 5, right? You will start to kind of visualize these things. For problem 4, and I'll switch back to blue, I've got 2 root 3 minus 4 root 5. This cannot be simplified. Root 3 can't be simplified. Root 5 can't be simplified. These are not like radicals, so we cannot combine them. So this is fully simplified. I'd also probably accept prime, but what it means is I can't do anything further to this. Next, I have 2 cube root of x squared y plus 3 cube root of negative 8x to the 5th y. So before we were doing square roots, now we're doing cube roots. That's going to give me 2 cube root of x squared y plus the cube root of negative 8 is negative 2. And this x to the 5th, if I look at x to the 5th, that's 5 x's. There's one perfect cube hiding in there. So one x is going to come outside, and I'm left with 2 under the radical and a y that can't be simplified. Now I see that these are right radicals. If I've got 2 cube root of x squared y plus a negative 2x cube root of x squared y, those both are like radicals, but it's hard for me to see how I could combine them. One way is to maybe factor out the radical. So I'd have 2 minus 2x all times the cube root of x squared y, but that's an unnecessary step that you don't have to take. You really can't combine these because one coefficient has a variable and the other does not. Let's take a look at our second example. I'm looking at the square root of, 5 square root of 4x cubed plus 3 cube root of 64x to the 4th. So I can simplify this. I'd have 5 times 2 times x root x. All of this is how this would simplify because I've got a perfect square hiding in this x, so one gets to come outside. 4 square root of 4 is 2, and I'm left with 1x under the radical. Then I have plus 3, the cube root of 64. Well, the cube root of 64 is 4. And if I take the cube root of x to the 4th, 1x is going to be able to come out, but another cube root is left under the radical. So now I have 10x root x plus 12x cube root x. And I can't simplify this any further because one of these is a square root and the other is a cube root. So these aren't the exact same type of radical. These are not like radicals. So this is fully simplified. So when we're multiplying roots, what we want to do is we're going to multiply what's under the radicals. That's our rule. As long as I'm multiplying radicals that are the same, so like the square root of 2 times the square root of 3, I multiply what's underneath them, it becomes the square root of 6. If I've got the cube root of 4 times the cube root of 3, that becomes the cube root of 12. When I cannot multiply them is if they have different powers. So I can't multiply the square root of 2 times the cube root of 4. I can't multiply those two together because one's a square root and the other's a cube root. So in order to multiply radicals, what we do is we multiply our coefficients, those outside numbers, together. And then we multiply what's under our radical and simplify the new radical if we can. So if I have the square root of 5 times the square root of 15, that becomes the square root of 5 times 15, which is the square root of 75. There's a perfect square hiding in 75. That perfect square is 25. And if you didn't see that, you could make yourself a little factor tree. It's what I recommend. I'd love to see one on a quiz or a checkpoint or an exam. So I'm going to take the square root of 5 squared times 3. So I'd have 5 root 3. For problems like this, we've got two options. I can simplify what's under the radical first, or I can simplify them at the end. It's totally up to you. I prefer to get the simplification out of the way. The square root of 8, that's going to be 2 root 2. And then I've got 2 times the square root of 2, sorry, times the square root of 4, which is just 2. So now I have 3 times 2 times 2 times 2. Well, that gives me 6. 6 times 2 is 12, times 2 is 24. I've got 24 root 2. For this last example, I have the square root of 32, and 32 is 16 times 2, which is 4 times 4, right? This is my biggest perfect square. It's got 2 2's hiding in each of those. So this is going to become 4 root 2. So I have negative 4 root 2 times 5 root 2, which gives me negative 20 root 4. Well, the square root of 4 is 2, so I've got negative 20 times 2. My answer is negative 40. Examples are about multiplying radicals that are in the form of a binomial. So examples where we're going to need to use the distributive property and where we're going to need to FOIL. So for example 1, if I have the square root of 3 times the square root of 7 plus the square root of 5, I'm just going to distribute this. The square root of 3 times 7 plus the square root of 3 times 5. And again, I'm doing an extra step here. The square root of 21 plus the square root of 15 is how that would simplify. And then I see, can I simplify the square root of 21? No, it's the product of 2 primes. Same thing with the square root of 15. So our answer here is complete and fully simplified. For problem 2, we need to FOIL. So I'm going to do 3 times 5, which is 15, plus 3 times the square root of 2, plus the square root of 2 times 5. I always write that as 5 root 2. We always want the constant in front because if I did the square root of 2 times 5, it's kind of hard to see, is that 5 under the radical or not under the radical? Also, I mentioned we treat radicals like variables, and variables always come after our constant, and so do roots. And then lastly, the square root of 2 times the square root of 2, that gives me the square root of 4. So I have 15 plus 3 root 2 and 5 root 2, 8 root 2, plus the square root of 4 is 2. So I'd have 17 plus 8 square root of 2. More foiling. One thing I want you to notice about problem 1 is this looks really similar to the product of a sum and a difference that we saw before in module 4 and 5. So something of the form x minus 1 times x plus 1. If we FOILed that all out, we'd get to x squared minus 1, meaning there's no middle term. So let's see what happens for example 1. I've got the square root of 10 times the square root of 10, so I have the square root of 100 minus the square root of 30 plus the square root of 30 minus the square root of 9. That means 10, these terms cancel. The square root of 9 is 3. I'm left with 7. So in this case, all of my radicals went away. Isn't that so nice? For problem 2, I have 2 times the square root of 5 plus 2 times the square root of 3 minus the square root of 35 minus the square root of 21. And this is fully simplified because I can't simplify the square root of 35 or the square root of 21, and none of these are like radicals, so I can't add them. When it comes to division, remembering that radicals are rational exponents, and our rule from chapter 4 was that they distributed over division. The same is true for radicals. If I want to take the square root of 16/25, that becomes the square root of 16 over the square root of 25. That's 4/5, right? We can simplify that. So if I have the square root of 49 over the square root of 81, that becomes the square root of 49 over the square root of 81, which would give me 7/9. It's not necessary to know all of the square roots that are out there, the perfect squares that are out there and exist, but you want to know at least like the ones between 1 squared and 10 squared. It'll make your life easier. Next, I'm taking the 4th root of 81 over the 4th root of 16. The 4th root of 81 is 3. The 4th root of 16 is 2, so I have 3 halves. For problem 3, I have the square root of 6 over the square root of 49. Well, the square root of 6 can't be simplified, but the square root of 49 is 7. If I take the cube root of negative 8 1/25, I just put that negative on the top. Remember, I don't want to put the negative on the top and the bottom because two negatives make a positive, and this is a negative number. The cube root of negative 8 is negative 2, and the cube root of 125 is 5. So our final answer for this would be negative 2/5. Now, for a very important concept. We need to talk about rationalizing the denominator. That means removing radicals from the denominator of a rational expression. And we do this by multiplying the numerator and the denominator by the smallest radical to produce a whole number in the denominator. So if I had 1/3 and I want to get rid of that square root of 3, I'm going to multiply by the square root of 3 over the square root of 3. Because the square root of 3 over the square root of 3, well, that's just equal to 1, right? Remember, any fraction, any number times 1 is just itself. So when I do that, I take 1 times the square root of 3, which gives me the square root of 3. And then I've got the square root of 3 times the square root of 3, which is the square root of 9. So I would get the square root of 3 over 3. This is a rationalized number. We don't like radicals in our denominators. So let's practice a bunch. For problem 1, I've got 3 over the square root of 7. So I'm going to multiply that by the square root of 7 over the square root of 7. You just pick the smallest denominator, the smallest radical. The only radical here is the square root of 7. That's my only choice. So I have 3 square root 7 over the square root of 49. That gives me 3 root 7 over 7. That's my final answer. It's not super satisfying. Does it look much nicer? No, but my radical's not in the denominator because these are now on my ooh list, things we don't like. For problem 2, remember that we're picking the smallest radical to get the denominator to be a whole number. I don't really care about that square root of 2 in the numerator. I only care about getting the square root of 5 from our denominator. That gives me 5 root 10 over the square root of 5 times the square root of 5. That's the square root of 25, which is 5. We'll see that in my next step. So I have 5 root 10 over 5. Those 5 cancel. I'm left with the square root of 10. For problem 3, I could go ahead and multiply by the square root of 12. But what if I went ahead and simplified the square root of 12? Because I know the square root of 12 is 2 root 3. So the smallest radical I see is the square root of 3. That gives me negative 6 square root of 3 over 2 square root of 9. So I have negative 6 square root of 3 over 2 times 3. Negative 6 square root of 3 over 6. Those 6's cancel. I'm left with negative square root of 3. So that's how we rationalize denominators when there's only one radical in our denominator. What about if there's more? Or what about if my denominator isn't just a radical by itself? Apparently that's in 2 slides. 2 slides. Now let's simplify these. I've got negative square root of 18 over square root of 125. The square root of 18 becomes 3 root 2. The square root of 125 becomes 5 root 5. So I need to multiply by the smallest radical to get rid of the denominator. That's going to be the square root of 5. So I have negative 3 square root of 10 over 5 times the square root of 25. So I have negative 3 square root of 10 over 5 times 5. Negative 3 square root of 10 over 25. This also works with variables. So I have the square root of 50m to the 4th over the square root of p to the fifth. The square root of 50, that becomes 5 root 2, but I've got m to the fourth, that becomes m squared. So I have 5 m squared root 2 over p to the fifth, that's going to be p squared root p. So I have to multiply by the square root of p on the top and the bottom to get rid of that p. So I've got 5m squared square root of 2p over p squared square root of p squared. That's going to give me 3 p's in my denominator. So I'm going to have p squared times the square root of p, which is p. So my final answer would be 5m squared root 2p over p cubed. Again, we don't want rationals and radicals in our denominator, and that's why we are going through this whole process, which we'll see more of in college algebra and pre-calc. So if I have a radical expression, and it's not just a radical in the denominator, but it's a constant as well, if I multiplied by just the smallest radical, that wouldn't get rid of my radical. So what do I need to do? Well, you're going to have to multiply by the conjugate. When you multiply by the conjugate, the middle terms go away. We saw in a few examples ago how when I multiplied the product of a sum and a difference, also known as conjugates, together, all my radicals went away. So if I'm trying to rationalize a fraction like the one above, instead of multiplying by the square root of 2 over 2, I'm going to multiply by 1 minus the square root of 2 over 1 minus the square root of 2, because this is the conjugate of our original denominator. And what's going to happen here is I'm going to get in my denominator 1 minus the square root of 2 plus the square root of 2 minus the square root of 4. And what we'll see here is that my radicals canceled out. So I've got 1 minus the square root of 4, so I've got 1 minus 2 in my denominator. So I'd be left with 1 minus the square root of 2 over negative 1, which in this case would just change the signs. But I was able to get that radical out of our denominator. So we multiply by the conjugate. Here is a very detailed worked out example, so you have it to go back to as a reference. So let's say we took this fraction. I've got 7 over 5 plus root 3. We have to multiply by the conjugate of 5 plus root 3, which is 5 minus root 3. When I do that, in the top I'm going to distribute, and in the bottom I need to FOIL the whole thing. If I distribute and then FOIL, all my middle terms cancel out. So I have 5 squared minus the square root of 3 squared, otherwise known as the square root of 9. And then I'm left with this constant in my denominator. So let's practice doing a few of these on our own. I have 3 over 1 plus the square root of 2. So that we multiply by 1 minus the square root of 2. That gives me 3 minus 3 root 2 over 1 minus the square root of 2 plus the square root of 2 minus the square root of 4. So I have 3 minus 3 root 2 over 1 minus 2. That's going to give me 3 minus 3 root 2 over negative 1. So my signs change, and I have negative 3 plus 3 root 2 is my final answer. For example 2, I'm going to multiply by 4 plus root 3, because that's the conjugate of 4 minus root 3. So I have 20 plus 5 root 3 over 16 plus 4 root 3 minus 4 root 3. Again, what I'm doing is I'm FOILing 16 plus 4 root 3 minus 4 root 3 minus the square root of 9. So I have 20 plus 5 root 3 over 16 minus 3. So 20 plus 5 root 3 over 13. And then you should always check to see if you can simplify your fractions any further. In this example, we cannot. In example 3, things are a little bit different because I have not one but two radicals. Fear not, we're still just going to multiply by the conjugate. That gives me 2 root 5 minus 2 root 3 in my numerator. I'm going to have the square root of 25 minus the square root of 15 plus the square root of 15 minus the square root of 9. When I FOIL it out. So I have 2 root 5 minus 2 root 3 over 5 minus 3, which is 2. So I have 2 root 5 minus 2 root 3 over 2. I could think of this as factoring out a 2 from my numerator, so I'd have 2 times the square root of 5 minus the square root of 3 over 2. So those 2's are going to cancel, and I'm left with the square root of 5 minus the square root of 3. And I'm slowly running out of room, as you can see. For problem 4, I have the square root of 2 minus the square root of 3. So we're going to multiply by the square root of 2 plus the square root of 3 on the top and the bottom. So I have negative 3 root 2 minus 3 root 3 over the square root of 4 plus the square root of 6 minus the square root of 6 minus the square root of 9. So this is going to simplify to a 2 and a minus 3. My middle terms cancel. So I have negative 3 root 2 minus 3 root 3 over 2 minus 3. That becomes a negative 1. That means I then have to change my sign. So I have 3 root 2 plus 3 root 3 for my final answer.